Hello, my name is Jani, and today I'm going to be presenting overdamped mechanical oscillators. This is for Math-024, and I'm in section 22D in fall 2020. So to start off with, what are mechanical oscillators? So different differential equations can represent many different models, and one of them are mechanical oscillators, which are a kind of physics model. I've drawn it out at the bottom right, and you can see there's a mass connected to a wall with a spring and a dashpot. And in this physics model, we've made a few assumptions. The wheels have assumed to have no friction and no mass. The spring force is proportional to the displacement from rest, and the displacement is called U of t. So creating a system of dEs. So we can do this by first using Hooke's law of physics to get the spring force, which is negative Ku. In this case, K is a spring constant, Newton over meters. Next, we know that the dashpot force is proportional to velocity. And so we can do F equals negative B U prime, and U prime is the derivative of U, and in this case, B is the damping constant. Finally, U of t uses Newton's second law, which is F equals ma. So from ma, we get m times the second derivative of U, and that's equal to the sum of all forces. So now, in order to derive our second order differential equation, we can simplify mu prime prime equals the sum of both forces, the spring force and the damping force, which is equal to negative Ku minus Bu prime. So by simplifying and dividing by m on both sides, we end up getting the equation u prime prime plus b over m u prime plus k over mu equals 0, where u prime prime is the inertia or acceleration, b over mu prime is the damping force, and k over mu is a restoring force. In this differential equation, when b is over 0, the motion of the mass is called damped, and the diagram for u of t versus t is shown below. As you can see, it oscillates until there's no longer any displacement or movement, basically. So now let's do an example problem. So consider a mass of 2 kilograms on a table attached to a spring on the wall. It takes a force of 1 Newton to pull this mass 0.25 meters. Further, the damping constant B is given as 4. Create a dE. So to solve this, we would do K is equal to Newtons over meters, which is 1 over 0.25 meters, and we get 4. The mass is given as 2 kilograms, and B is given as 4. Plugging this into the dE we end up getting u prime prime plus 2u prime plus 2u equals 0. In this problem, we could have also been given two initial conditions, such as like ICs, and this would help us solve for a complete initial value problem. Finally, these were the references I used to create this presentation, and thank you for watching.